Welcome to the sixth lecture on parallel programming. Today we're going to deal with some advanced OpenMP and performance issues with OpenMP. But first of all, before we go into details, let's cover some miscellanea, like environment variables and API calls, to get that out of the way. So you already know one or two environment variables that influence the behavior of OpenMP programs at runtime. The most important one, arguably, is OMP num threads, which determines how many threads are to be used in parallel regions if the number is not set from the code. And we'll cover one or two ways to do that from the code as well. The standard way is to just set OMP num threads. OMP schedule lets you determine the parallel schedule to use for runtime scheduled loops. So if you use a schedule of runtime on a parallel loop, then the contents of the OMP schedule environment variable determines at runtime how these iterations should be distributed on the threads. The schedule that you provide for OMP schedule also takes a modifier. I didn't mention that when we covered the scheduling types, so I'm doing it here. The modifier can be monotonic or non-monotonic. This determines whether iterations are fed to threads in the original order. So usually we're doing this with loops, and if you specify monotonic, it means that every thread gets, of course, a subspace of the full iteration space, and that iterations are fed to the thread in ascending order. Or monotonic order for that matter. So if the loop is backwards, they are fed backwards. If you specify non-monotonic, it may mean that there are backward and forward jumps, and you cannot rely on the iterations per thread to be monotonic. There's also another modifier called SIMD, which determines that the chunk size of the schedule should be a multiple of the SIMD width, which could be advantageous if you do SIMD vectorization, and we'll come to that a little bit later. You know also the facilities in OpenMP for binding threads to cores and processors. This is OMP places, determines the unit for placement of threads, and we've covered that in detail in the last lecture. And OMP proc bind, which says how the threads should be put into those places. We've also come across the OMP stack size variable that lets you determine the per thread stack limit. As you know, local variables of threads are put on local stacks. These stacks have limited sizes or limited size. So here you can determine what size should be available per thread. It's an integer plus a size denomination like byte, kilo, mega, or gigabyte. OMP dynamic is interesting. It allows or disallows, via setting it to true or false, dynamic adjustment of thread count by runtime. So there are some OpenMP runtimes which can determine whether or not your code is running effectively. So probably if you're spending a lot of time within the OMP runtime, the runtime can detect that and reduce the number of threads automatically. Often that's not what you want, because it's an automatic mechanism that's like abstracted from your view, but it might be interesting in a production setting. Of course, not all OpenMP implementations actually support that. OMP wait policy could be interesting in situations where you share a node with others. You can set it to active, passive. And OMP wait policy determines what a thread should do when it's waiting, for example, in a barrier. Passive means that threads go to sleep as soon as possible, so they free resources, while if you set it to active, then the thread keeps running and spinning, waiting for some event to give it some work again. So this could be interesting if the node you're working on is not your own. If you share the node with others, then it could be interesting to set it to passive because you don't want to block resources for others just by waiting in a barrier. On the other hand, if your resources are exclusive to you, if you own the node, at least for the time of the job you're running, then it might be interesting to set it to active, because this reduces the overhead for barriers. The default setting of this variable is implementation defined. OMP display affinity gives you a way to print at runtime the affinity info, so which thread is pinned to which part of the hardware. You can set it to true or false. It's a very nice way of looking at your affinity and whether it's done the way you want it to. There's even another variable, OMP affinity format, that you can use to specify the exact output format. So there's a lot of options, and please consult the standard to look up what can be done here. So this is a very flexible option, and it's nice. You don't have to write your own program to print the affinity. You can let the code do it by itself, just by the automatic OpenMP mechanism. So there are some more environment variables, but this is the most important stuff that you need for daily work. Now, beyond environment variables, we also have some API routines. And again, there's more than what I can tell you here. So these are the most important ones. We have OMP set num threads. So this sets the number of threads in the subsequent parallel regions where there's no num threads clause, which means OMP num threads variable is not the only way you can influence the number of threads. You can also set it from the program. OMP get num threads gives you the number of threads in the current team. We've used that already. And OMP get thread num gives you the ID of the calling thread, which is always from 0 to number of threads minus 1 without any gaps. OMP get num procs delivers the number of available processors on the device, which might be interesting sometimes. OMP in parallel delivers true or false, depending on whether you are executing within a parallel region or not. So this is sometimes handy if you want to disable parallelism when you detect that you're already inside a parallel region. So then you don't want to open up any more threads, so you want to disable it. That's where OMP in parallel comes in. It's mostly useful if you write libraries. OMP display affinity is a way that's very similar to the affinity variables I showed you in the slide before. It just prints the affinity info on the standard output. And then there are two timing functions. Of course, I told you how to measure walk log time from your program with a POSIX compliant function, but OpenMP has also its own timing function, which is OMP get W time. It gets you a timestamp, just like our get timestamp routine from the example codes. And OMP get W tick gives you the seconds between successive timestamps. So that's like a measure for how fine-grained you can measure the time. That's quite interesting. So if you know that you'll always be using OpenMP, then you can also use these OpenMP API routines to measure the time. All right, so much for technicalities. Now we get to the meat again, and we start with more facilities for OpenMP synchronization. So last time we talked about critical regions, named critical regions, and atomic constructs, but these have their limitations. For example, what if you need a lot of named critical regions, like 1 million of them? Okay, they have to have distinct names, and there's no way to have an array of names in OpenMP. Also, if you want to use atomic, what happens if you need more than just a simple variable update within the atomic region? So there are some cases where atomic and critical just don't do it, and this is where locks come in. So what's a lock? A lock is something that protects a shared variable, or generally a shared resource. So in this visualization here, we have two threads, and they try to get hold of this shared resource, this shared variable, and let's assume one thread comes first. It acquires the lock, in this case symbolized by the key, while the other one has to wait. Now there are two possibilities for waiting here. The first option is a blocking wait, which means the thread that came last, that has to wait, waits until the other thread has finished its work, playing with whatever is there at the resource. And there's also the option of non-blocking wait, which means the other thread, which came late, doesn't just wait, it can do other useful stuff, useful work, and then two threads do work while the lock is taken. So whether or not you're using blocking or non-blocking semantics, both supported by the OpenMP standard and by the lock facilities. So let's look at how this is done. There are two types of locks in OpenMP, the simple type and the nestable type. If you want to do anything with locks, you need to know that these locks have to be established using predefined data types. And these are called OMP lock-T and OMP nest lock-T. So for the next one or two slides, I'm going to denote anything that's green is simple locks, anything that's blue is nestable locks. In C and C++, these are predefined data types, actually structures. And in Fortran, these are integers of a certain size. In order to use a lock, to do anything with a lock, you have to initialize it. And you do that with the OMP init lock or OMP init nest lock call. So any lock that you want to use, you have to initialize it first. Now, the objects or objects that a lock protects, that's something defined entirely by the programmer. So there's no syntactic or semantic connection between a particular lock variable and a particular resource. That's all up to you in your program. Okay? The only thing you need to know is a lock must be initialized and the initial state of any lock is unlocked. Now the main difference between a nestable, actually the only difference between a nestable lock and a simple lock is that a nestable lock or nested lock may be locked or unlocked multiple times by the same task or thread. So which means if a thread hits or wants to set a lock, it can do so. And if it tries to acquire the same lock again, it is allowed if it's a nested lock. Okay, and then of course, if the thread wants to unlock the lock again, it has to do it the same number of times as it's called the lock routine. Now, in case you want to get rid of locks, and that may be an option or may be necessary because you may want to establish or create a huge number of locks, you can destroy them. So using OMP destroy lock or OMP destroy nest lock function. So these functions disassociate an initialized lock variable from a lock. All right, so that's just for establishing, initializing locks and destroying them. So how do we actually use them? And now I'm going to restrict myself to simple lock routines. The simple lock routine is OMP set lock. So the set lock routine sets the lock, it acquires the lock, and if it blocks if the lock is not available. So if another thread has already taken the lock, then the second thread that wants to acquire it has to wait. It's a blocking routine. If the lock is available, it sets the ownership and continues execution after the OMP set lock call. Now, once you're done with the variable or the resource you want to acquire, then you have to unset the lock with the OMP unset lock function. It releases the ownership of the lock, and of course it's only allowed to call this routine if you actually own the lock. So this is unlocking. And so these two routines are for the locking semantics I described at the beginning. Of course, if you don't want to wait if the lock is acquired by somebody else, but you do want to do something else, useful work, then you may also test it and go somewhere else. And this is done with the OMP test lock function. If a lock is set and you test it, then the function just returns false. But it returns, and you can go about and do whatever you want, just not use the protected resource. If the lock is free, the test lock function will set the lock for you and return true. So this is the way to actually make threads test a lock, whether it's locked or not, and if it's already locked, do some other useful work. Here's an example for how to use locks in a situation where atomics and also named critical regions will not do the trick. So what we want to do is we want to update the columns of a matrix. And to do that, we have this matrix M, n by n matrix. We set up an array of locks called locks. Data type is OMP lock-T, so these are simple locks, also of length n. And in our minds, there's nothing in the syntax of the program that associates these locks with a matrix, but in our minds, that each of these locks is associated with one column of the matrix. Now, within the parallel region, the first thing we do is initialize all the locks. So with this loop over all n locks, calling OMP init lock with the address of each individual lock. And then in the actual work loop, which is a work shared for loop, we go from 0 to k. We calculate first something from a function called calc, and this result c is then used to be fed into a function f, and this function f, this value that the function delivers, is used to update a column of a matrix. And this loop down here from j from 0 to n actually updates the complete column. Now, the problem here is that you don't know what the outcome of the callCalc function is. So if you don't do anything, if you don't synchronize the access to the columns, then it may be that multiple threads update the same column at the same time, which would give us a race condition, and that's not good. So we need to protect each column. Now, we cannot do this with named criticals because we don't know how many columns there are. It's a number n, so it could be defined at runtime. We don't know how many there are. Also, it's not good to use atomics because it's a whole loop that you want to protect. So the solution here is to use locks. Since every lock number c protects column c, we can just set the lock before we enter the update loop and unset the lock after. Which means if two threads want to update different columns, there's no problem. No one is waiting. They just set their individual locks and go about their work. But if two threads want to update the same column, one has to wait at the setLock function. Now, of course, if you think about this, and you can do this as homework, you may come up with an even better solution, performance-wise, and also a simpler solution that expresses more of the elegance of OpenMP. But I'll leave you to that for homework. Okay, so much for synchronization. Now, the next thing I'd like to cover is SIMD support. You may remember that SIMD stands for Single Instruction Multiple Data Processing. So it's a data parallel feature of modern microprocessor instruction sets. Just a little reminder what SIMD is. In SIMD, we have special machine instructions on the processor that allow data parallel processing of vectors. In this case, we have vectors of 4 elements. Typically, these vectors are stored in registers on the CPU, and the CPU has instructions, in this case, add instructions, for example, to add 2 full vectors instead of just 2 elements of some data type in order to get a result. So in this case, this quadruples the available add peak performance of the CPU. And actually, SIMD is one of the main drivers for peak performance in modern hardware. Now, what are the challenges that we keep encountering with SIMD? First of all, it's the compiler. The compiler has to know that it's safe. The compiler has to be able to prove that successive iterations of the loop are independent in a way that enables this kind of parallel execution. And sometimes the compiler cannot see this because the base language stands against that, or because you somehow obstructed the view of the compiler on the data structures with your programming style. There are many reasons why the compiler doesn't see that a loop is actually vectorizable. So how do I tell the compiler that it's okay, go ahead, do the SIMD thing, okay? Before OpenMP SIMD functions, there was no standardized way to do that. Now, secondly, if you have parallel loops with certain chunk sizes in OpenMP, then there may be an interaction of the loop chunk size and the SIMD width. Imagine you had a CPU with an 8-wide SIMD unit, so 8 elements per vector register, and your chunk size would be 7. That would be quite unfortunate because you would not be able to utilize the full width of your SIMD registers. So this interaction is unclear. If you have a loop that has normal loop variable, it's totally clear to the compiler what you want to do. Okay, this is the direction in which you want to vectorize, in which you want to apply the SIMD instructions. But there may be other variables that also have an inductive nature, that are incremented by a certain constant amount from iteration to iteration. And this is a little bit difficult in terms of SIMD. How should the compiler know these variables are actually fine? They are also increment from iteration to iteration with a certain increment. So how should the compiler handle it? Also, there's no well-defined way to tell the compiler what's going on here. And finally, very difficult problem. How do you make SIMD available for function calls? Let's say you have written a very fast and convenient function for calculating Bessel functions, and you want to do that for parallel or 8-way parallel using the SIMD feature. How do you do that? Before OpenMP SIMD, there was no way to do that. All right. So SIMD has nothing to do with threading, of course. So one may ask, why is it in the OpenMP standard, which is all about threading? However, SIMD has everything to do with data parallelism, and OpenMP also deals with data parallelism. It's actually a natural evolution, natural development that SIMD found its way into the OpenMP standard. So it has been there since version 4.0, and there have been some improvements since. We're now at version 5.0.1, and we'll shed some light on some of the interesting SIMD features of the OpenMP standard. So the simplest construct we have in OpenMP for SIMD is the SIMD construct for loops. It's something like user-mandated vectorization. If you put pragma OMP SIMD in front of a loop, it enables the vectorization of the loop by telling the compiler, go ahead, there are no dependencies here. Okay, you can rely on me, just believe me. And of course, you should not lie to the compiler. If there are dependencies, while you're telling the compiler they're not, then your results may be wrong. Here's a very, very simple example. There's a loop setting an array A to a scalar times an array B, okay? And of course, you may think this is a loop that's very easy to vectorize because the iterations are independent. Iteration I is independent from iteration I plus 1. However, in the C and C++ language, this is not a given. In the C and C++ languages, A and B, the two arrays, can overlap in any possible way. And it may be that B of I is actually A of I minus 1. Now, if that happens, this loop does have dependencies, actually very severe dependencies that prevent vectorization. So I can tell the compiler that this doesn't happen, that the arrays don't overlap and also other dependencies don't apply by just writing pragma OMP SIMD in front of the loop. Okay, this takes away the bad vibes for the compiler and tells the compiler it's fine, assume there are no dependencies, and do whatever you can to SIMD vectorize this loop. Now in practice, this is a good thing. However, it may also backfire. So it's not guaranteed that you will get better performance, but it's actually worth a try if the compiler says, I can't vectorize this loop because there's a dependency and you know there is none. What are the prerequisites for a loop to be SIMD vectorizable? It has to be countable. So on entry to the loop, the compiler has to be able to generate code that determines the length of the loop. So loops in which the size is determined by a condition that's only that depends in some way on the data that you're crunching in the loop, this will not do. It has to be an innermost loop. SIMD cannot be applied to outer loops, and it must conform to the standard for loop style of OpenMP work sharing. So it has to be in a form that can also be digested by the OMP4 construct. Now the SIMD construct has some clauses that you can apply. The most important ones are SIMD-len, linear, and safe-len, which we'll cover in a minute. There's also reduction, private, first private, and a couple more that are very similar to the ones you use on word-shared parallel loops, and which also have the same meaning, so we don't cover them here. The SIMD-len clause lets you specify the preferred SIMD width in iterations. That's actually a hint to the compiler that it is free to ignore. But for example, if you say SIMD-len 4 here, the compiler should try to produce a loop that is vectorized with instructions that have a SIMD vector size in elements of 4. The safe-len clause specifies that there are no loop carrier dependencies for vectors of the specified size or below. Now that may seem a little bit esoteric, so I have an example here. In this case, we update a vector b with scalar times b of I minus k. Now, if at compile time the value of k is not known, it is very dangerous to vectorize this loop. Just imagine that k were 1, then we would have b of I equals s times b of I minus 1, which would not be vectorizable right away. So the compiler will usually refrain from vectorizing such a loop unless you tell it that it should vectorize it with a safe len of 8. And this means that this code is safe to vectorize with SIMD instructions up to a width of 8 if k is greater or equal than 8. So it means that if there's a loop carry dependency, the distance of this dependency is greater or equal than 8. And then it's safe to vectorize with a SIMD width up to 8. So it's actually something that's very convenient if you know the value of k, but the compiler doesn't. Linear is a very interesting clause. It specifies a linear relationship of induction variables, which are specified in the list, to the loop counter. In this example, we have a reduction loop. So it's pragma OMP SIMD reduction. Remember, this is not a workshed for loop. It's a SIMD loop. And you use the reduction clause just like the same way as with the for loop. So it has the same meaning. And the reduction variable is s and has the same semantics as with parallel loops. The interesting part of this loop, however, is the linear clause. And here we specify linear p:2. Now, what does that mean? P is a variable that's incremented in each loop iteration by an increment of 2. And we use it in some way within the iteration. Now, if the compiler wants to vectorize this loop, then the p variable will give it a hard time because it's not entirely clear where p, what is done to p and which relation it has to the loop iteration counter. Using the linear clause, you can tell the compiler that p is linear in the iteration counter I, and that the relationship is 2 to 1. So each iteration, each scalar iteration of the loop, the p variable is incremented by 2. And if you tell that to the compiler, it's very easy for it to vectorize the loop. So this enables the compiler to employ SIMD in presence of induction variables. Of course, you have to make sure, or the compiler has to make sure, that the result of the whole construct, the whole loop, is the same as if it were executed sequentially. So after the loop, the induction variable has the same value as in serial execution. So the value it would have in the last iteration of the loop if the loop were executed sequentially. You can also use the linear clause in workshed for loops. If the compiler has any problem dealing with induction variables, then you can use the linear clause there as well. So up to now, we've been dealing with pure SIMD loops, the SIMD construct that applies to the immediately following for loop, and there was no threading involved. Certainly, you can combine the SIMD feature with work sharing, and this is the case for the SIMD clause. SIMD clause is used on for loops. You can just write pragma OMP for SIMD, and then whatever clauses apply to for and to SIMD. Now, an interesting detail is that if you specify a schedule for the loop, then you can prepend the static schedule, or any schedule actually, with a SIMD prefix. And this means that the chunk size of this loop, if you specify one, is extended to match the next SIMD width multiple. So this makes it easier for the compiler to generate loop code with SIMD instructions. Let's say the chunk size was chosen to be 7, but your SIMD width is 8 on the CPU. Then you'd like the static chunk size to be 8, so that the SIMD registers are utilized in their full width and not just by 7 out of 8. Another detail here is shown in the loop kernel, in the loop body. Here we update, or we write to a of I the result of exponential function of b of I. Now, this is inside a SIMD parallel loop, so we actually expect from the compiler to handle this situation. Now, what does it have to do? It has to look for an implementation of the exponential function that's actually SIMD compatible. So it has to look for a version of exp that takes vectors of some size and calculates the exponential function for each entry of the vector. It will use the SIMD version of the function if one is present, if one can be found. Some compilers do that automatically, even if you don't specify any SIMD clause. For example, the Intel compiler has, if you have the Intel compiler, it comes with a so-called SVML library, the short vector math library. And this library implements these functions for short vectors. So without doing anything for the Intel compiler, loops like this can actually be vectorized. Now this brings us to a very important topic with respect to SIMD, and these are SIMD functions. What happens if I do want to write functions like this exp without them being present in a library in the first place? So can I write such functions? Can I write functions that can be called in a SIMD vectorized loop and produce more than one result at the same time in the SIMD kind of way? And we can. OpenMP gives us this functionality. So functions and subroutines can be declared as SIMD vectorizable and can be called from SIMD loops. Here's a simple example. The function is hyp3d, and it calculates the sum of squares of three arguments, k, l, and m. So simple enough. Now I've denoted this function to be SIMD vectorized. So pragma OMP declare SIMD. The declare keyword is important here. And this means that the compiler will try to produce a SIMD version of this loop. Now, how can I use this? In the main program, I have four arrays, A, B, C, and HIP. And I have a parallel for SIMD vectorized loop here. And I want to calculate, I want to call this function for every iteration of the loop by handing to the function the three arguments A of I, B of I, and C of I. I'm doing this as usual, but the SIMD clause here in this parallel loop tells the compiler, try to find a function hyp3d that is actually SIMD compatible and SIMD vectorized, and call it in a SIMD way, which means the function is not called for every individual loop iteration. The function is called for 2, 4, 8 or more iterations at once, using not scalar variables, A of I, but vectors, A of I and A of I plus 1, for example, if the SIMD size is 2. So if the SIMD size is 2, then the hyp3d function will be compiled, because it's declared as SIMD, to accept vectors of size 2 for the three arguments k, l, and m. And when it's called from a SIMD vectorized loop, then three short vectors of size 2 will be handed to the hyp3d function. And this is all automatic and under the hood. Of course, the compiler must also produce a normal, standard, non-SIMD version of the function, because it's entirely possible that from a different part of your program, you want to call this function in a non-SIMD context. Okay, so it has to produce scalar versions as well. And that's by far not all there is to SIMD in OpenMP. Here's an example for a more complex scenario. We have a similar function as before, hyp3d, now with _I. And this function doesn't have three scalar arguments. It has three vectors or pointers to double and an integer index as an argument. And the way we want to use this function is shown down here. We want to call it with the three vectors as actual arguments. These are just double vectors, A, B, C, and an index I, which happens to be the loop index of the loop. And this should be done in a SIMD kind of way. So in this case, we actually want to give the function the access to the complete vector and tell the compiler that the arguments A, B, and C, the first three, are vectors that should be handed to the function as is, and that I is an induction variable that is incremented in the direction of the SIMD vectorization by 1 in each scalar loop iteration. This is done by the linear and uniform clauses up here when we declare the function. So linear S1 means that the S index has a linear relationship to the vectorization direction in this case, and that it's incremented by 1 in each SIMD, in each scalar iteration of the loop. So then the compiler knows what to do with this S. It has to be incremented for the next SIMD lane in the sequence. However, we also have to tell the compiler that P, Q, and R are pointers or arrays that are handed in their entirety, so as objects to the function, or in this case as pointers, of course, and that they are left untouched. So uniform means that they don't change when the SIMD index increments P, Q, and R. So, and then in the function, we can just write P of S, Q of S, and R of S and do the arithmetic and return the result. There's another detail here. There's another detail here that shows how we can produce more than one version of a function by using the SIMDlen clause. I'm using just a duplicate of this declare SIMD directive with SIMDlen 4 and SIMDlen 8 respectively. This means the compiler is instructed to produce two versions of the loop, one for length 4, one for length 8. So this means if in any part of the program the compiler chooses a SIMD length of 4 and somebody wants to call this function, there's an appropriate version of this function. If a SIMD length of 8 is chosen in the calling function, then there's also an appropriate version of the pip3di function. So in this way, I can write a library that has a couple of pre-compiled SIMD compatible versions of the function ready-made for use by the linker. Okay, this concludes the part on SIMD. There's a lot more to be said about that, but this is enough to cover the basic functionality. Another interesting feature that came into OpenMP with the version 3.0 is tasking. Tasking is all about parallelism that's not in loops. So up to now, you may have the impression that OpenMP is all about parallel loops, and for a long time it was. However, there's a lot of stuff, for example, data, that's not in arrays. So there's list structures and tree structures, all kinds of flexible data structures where the elements are not arranged in a sequence order. Now, OpenMP gives you possibilities to address this kind of parallelism by tasking constructs such as task and task loop. These are the two that we're going to be covering today. The general pattern is as follows. We enter a parallel region. Of course, we must have threads. And then in order to generate tasks, customarily, a single region is opened where only a single thread enters. So usually only a single thread of the team actually generates task, while the execution of the task is then done by everyone. Within the single region, we have a task construct, which can be encountered multiple times, usually in a loop. And for each encounter of the task construct, a code that's within the task region with its associated data environment is packaged and put into a queue. Now, whenever threads are ready, when they are waiting at a so-called task scheduling point, then these threads can look into the queue and execute tasks as they see fit. Now, these task scheduling points are defined flexibly, so they can be, for example, automatic barriers, explicit barriers, and also points where a task is entered or left. So whenever there's something to be done inside the OpenMP runtime, or whenever a thread is waiting, it is eligible for task execution. So that's actually a very nice mode of operation. You have a single thread that produces tasks, and all the other threads, if they don't have anything to do at the moment, they are eligible for executing these tasks. The syntax is very simple, pragma OMP task followed by a structured block. In this example, we want to execute a function in a loop, but not in every loop iteration, but in every iteration only with a certain probability. Now we have an array of structures of type object called P. We enter a parallel region, we enter the single region, and within the single region, we have this loop from 0 to n-1. Within the loop, we calculate a random number. You know this from one of the exercises. It's just a number that is between 0 and 1. And then when this number is smaller than a component of the function, a component of the object at position I in the array P, then a task is generated. So depending on the values of these weights within these objects, this do work with function may or may not be called. Now, if you execute this in a standard OpenMP work-shared parallel loop, then you do a lot of useless work because lots of iterations are then empty, probably. Yeah? And you could also run into load imbalance problems. Now, in this case, it's very elegant. Whenever this condition holds, that the random number is smaller than the weight, a task is generated. And this task, in this case, only consists of a single call to a function do work with that gets the address of the current object, P of I. Now, there's a couple of questions here. What happens to variables as we enter tasks? Now, here's a variable I, which has been privatized. It didn't have to be, but I did it here explicitly to make this as explicit as possible. Whenever you have a private variable in an enclosing context, as is the case here for I, then this variable becomes automatically first private within the task. So I don't have to actually put it in a first private clause. Of course, I would like to do that because I has to be put into the data environment of this task. I is the position at which I want to access the array P. So whenever this task is packaged, when the code is packaged with the data environment, this I has to be part of this package, which means it has to be first private. Now, it doesn't hurt if I specify a first private clause on the task construct here, but I don't have to because I was already private in the enclosing context. P, however, is shared from the beginning. It's never privatized, so it stays shared. Nothing happens, nothing bad happens, and what I write as P here is just the global value I have in the program up here. So remember, private variables in the enclosing context are automatically first private per task. They are packaged within the task together with the execution, if you wish, the code of the task. Now, this seems nice, but there's more to it. So tasks, if you use them in your program, do not all have to execute the same code. You can have tasks executing in totally different parts of your program or doing totally different things. So here's an example in which we, in a simple way, overlap communication and computation. Instead of one array of objects, P of n, we now have two, P of n and Q of n. The beginning of this program is the same. We enter the parallel region, we enter the single construct, and the first thing we do in single is we kick off a task that does nothing but call a communicate function with a Q array. So we can imagine that this communicate function calls some message passing library and probably obtains the values of Q from some communication partner or partners. Now this is formulated as a task, so it is enqueued into a global queue, whereas it will be serviced at some time in the future whenever a thread gets to it. And the rest of this code is actually identical with the previous version. So we have the loop from 0 to n-1. We calculate these random numbers and we compare with the weights. So in this case, the global queue of tasks contains a number of do work with function calls plus this communicate function call. So there's nothing that forces you to execute the same code with different data in different tasks. Tasks can be totally unconnected. What happens if you want to combine parallel loops with tasks? Now, up to now, the only way we know for parallelizing loops is the for construct. And of course, you could also formulate this as tasks, but this would be cumbersome because you would be responsible for chopping the loop into pieces and making every single piece a task. It can be done, but it's really clumsy. So this is where the task loop construct comes in. It works on a for loop and it breaks the loop automatically for you into chunks and converts them into tasks. That's very convenient if you want to use tasks and loops at the same time and still use parallelism. Again, this is a variant of our previous program. We have, again, only a single array of objects Q. We have 3 arrays A, B, and C, each of length n, which we want to work on in this loop down here. And we have this communicate task, which also has to be performed. So what we do is first we kick off this communicate task to be serviced by some thread, and then we define a task loop, which means that the compiler is responsible for generating code that chops the loop into pieces, and each piece is going to be a task, and it will compete with the task up here for the resources on the team of threads. Now, the task loop takes a couple of clauses, and the most interesting one is grain size, which we specify to be 100 here. So this means this is a similar parameter to the chunk size in the loop schedule. It just tells the runtime in which chunks the loop should be chopped in order to produce tasks. By default, a task loop implies a so-called task group construct, which we haven't covered here. And this means that all tasks that are generated in the task loop will be finished before the loop is left. So whenever you do a task loop, by default, then the loop will execute as long as necessary to finish all the tasks. If you don't want that, it's actually like a no-wait clause, but not for threads, but for tasks. You can disable this behavior with a no group clause so that the loop can be actually left before by threads before the tasks have been serviced, but actually it's a reasonable default behavior. Okay, think of it as a barrier for tasks. All right, so up to now, we've only been thinking about tasks as things to do which have no mutual dependency. So one task and the next task and the next task didn't have any connection at all, apart from the fact that they might work on a similar data structure, but apart from that, there's no dependencies. In reality, many problems require that tasks can only be executed after other tasks are completed. So there are dependencies between one task and the next. Here's an example. I might have a compute function that produces a value, let's call it x, and this value might be used by other functions, for example, by a crunch function that does some computation and a statistics function that does some statistics collection. Now, it's entirely clear from this very simple diagram that the crunch and the statistics function, those two can run independently and in parallel, but they can both only start after compute has finished, because the variable x, the output of compute, is an input to crunch and to statistics. So this is a dependency that I'd like to make explicit to a program that uses tasks. In OpenMP, this is possible via the depend clause on the task construct. So this is exactly what I've denoted in the diagram on the left. I have a single construct and 3 tasks. One task calls compute and produces x as an output. And I'm denoting that by appending the depend clause without :x as an argument. So this specifies this task produces some x, and this x is an output that can be taken as an input by somebody else. There are two more tasks. One task is adding the outcome of the statistics function, which uses x as an input to accumulate to y, and the other task is also using x to call the crunch function and assigns it to z. Now, those two tasks, of course, need the computed value of x, so they cannot start unless the first task is complete. So we specify this in the depend clause. We say depend in :x in both clauses to denote that whatever was produced up here as an output is needed as an input here. Now, what this means to the runtime is that the second and the third task, they can run in parallel. They are totally independent, but they both depend on the first task. They will not run before the first task is complete. Now, that's a very simplistic example, but of course, this is a very powerful concept. So what the depend clause actually does, it defines the currently generated task, so the one that you generate with the task construct, as being dependent on a previously generated sibling task. So a sibling task is the one, simply speaking, that was generated in the same loop in the same single construct. And this dependency is valid if at least one of the items in the list has the same storage location on both tasks. So here in this simple example, we only had one relevant storage location, that was X. Of course, we could have more. We could also have arrays or elements of arrays here, and it is the task of the runtime and the compiler to figure out which one of those actually are dependent. So you could have, for example, a part of an array here in the output dependency, and a different part in the input dependency, and then if the compiler can prove that these are actually exclusive, there will be no dependency. So a prerequisite for this dependency to work is that the at least one of the items in the list has the same storage location on both tasks. Now, to get a little bit more light, shed a little bit more light on this, here's a more relevant example. This is a finite difference time stepping algorithm. So we have time steps, which are denoted by this loop t going from 0 to 99. And we have a loop from which goes from 1 to n minus 2. Loop index is I. So here's our array of values, a of 0 to a of n minus 1. Now what you want to do is we want to update the elements of this array by taking the neighbors of the current element I, a of I plus 1 and a of I minus 1, plugging them into a function, and the result of the function is then written to a of I. So in a graphical way, this is shown on the right. In order to get from time step 0 to time step 1, I take two values, which are two elements apart. I plug them into the function, and I produce a new value for the element in the middle. Now, of course, there's a lot of parallelism in this problem, because whenever the first row of updates has been done, I can actually do the second row of updates. Whenever two values have been produced, I can update the middle value. So I can express this dependency in OpenMP with dependent tasks. Now, the actual update is a of I equals result of the function. So that's my task, pragma OMP task. It depends as an input dependency on the left and right neighbor of the currently updated array value. So my in dependency is to a of I plus 1 and a of I minus 1. As a result of the task, a of I is produced. So that's my out dependency. Okay, so when this inner loop is traversed, I'm producing a bag of tasks. Of course, the runtime has to figure out at runtime which of these tasks can run. And the answer is the tasks can run that have their input dependencies satisfied. And this gives us a very elegant way of expressing parallelism for situations where using standard for loops would be very clumsy or cumbersome to use. All right, so much for parts of the OpenMP standard. I cannot stress this enough. I can only cover a small part of the standard here, but I hope I could give you a reasonable overview of what's possible. If you want to know more, there's literature and there's the standard. I cannot close without pointing out some interesting and important performance issues and their remedies with OpenMP. So first of all, we've already covered the cost of barriers, and it was also the topic of one of the exercises. You know that each implicit barrier and also explicit barriers cost some time. Also, waking up the team of threads costs time. Scheduling costs time, especially if there are tasks or dynamic loop schedules involved. So everything that pertains to parallelism and managing the parallelism costs time. Which means sometimes if there's not enough work to do between these costly management tasks, then performance could suffer. Now, this is the place for the if clause. The if clause can be applied to a lot of things in OpenMP. It takes any valid condition that's valid in the base language, so that delivers a logical value, true or false, and can be applied to lots of contracts. So, for example, it can be applied to the parallel region, the parallel construct. In this case, pragma OMP parallel if n greater than 8,000, this means that the parallel construct will only be executed as such in parallel if the condition is fulfilled. So in other words, if there's enough work in the loop. And of course, this value of 8,000, I have determined this, this is arbitrary here. So you have to know what you're doing here, right? There's no automatic mechanism that says only execute this loop in parallel if it pays off. Okay, this value of 8,000 is my expression of my knowledge about this overhead and the fact that I know that below 8,000 it doesn't make sense to parallelize this loop. It can also be used to suppress nested parallelism. So for example, if you write a library and you have serial and parallel versions of your functions, then probably you want to disable parallel execution if you know that you're already being called from within a parallel region. And this is done with the OMP in parallel function, which I've introduced in at the start today. So whenever OMP in parallel yields true, then I don't want to go parallel. So if not OMP in parallel, I want to execute my region in parallel. Okay. So this is also one interesting application of the if clause. There is, of course, it looks like black and white here. So whenever the if condition is false, then in our left example, the parallel region will be executed sequentially. But there's a whole gray area in between. Okay, if you want to run at 16 threads, the if condition means you're either running 16 or one thread. And that's a little bit harsh. So a less extreme option would be to use the num_threads clause to reduce the number of threads in a region whenever some condition is not met. Of course, this requires some more programming because you can't say if n smaller than 4,000 num_threads 2, else num_threads 8. So this is something you can't express in OpenMP. So you have to do some more programming there, but this would be the less extreme option. There's a gray area between one thread and all threads. One recurring problem that's often overlooked is granularity that's too coarse. Sometimes you do have enough work to amortize the overhead of parallelism. However, the chunks in which the work is put together or lumped together are so coarse that there's no efficient way of distributing the work across threads or tasks. So in this example, we have a two-way loop nest over L and K, and all we do is actually add elements of a matrix, and we do this in a parallel loop with static schedule and a reduction clause. Well, simple enough. However, if this is a situation, we have a 6x6 matrix and 4 threads, then what happens, because we only parallelize the outer loop, the L loop, which goes from 0 to m-1, if m is just 6, but we have 4 threads, then this is what could happen. The first 2 threads get 2 rows of the matrix, while the last 2 threads, 2 and 3, get only 1 row. So this is a severe load imbalance. Not every thread has the same amount of work. Now, it's not that there's not enough work in this loop. We could find a way to distribute the work more evenly across threads if we only could extend the parallelism from the first loop to both loops. And this is exactly what the collapse clause can do. The collapse clause, it has an argument integer n, coalesces perfect n-way loop nests. So the basic code is actually exactly the same, but I'm adding the collapse clause here to the parallel OMP4 construct. And what it does is it takes the next n, in this case 2 specified loop levels, and coalesces them into one big loop. So that's what happens here. Instead of letting a chunk per thread end at the end of a row, you can now have transitions between threads in the middle of rows because the two loops have been coalesced into one big loop. And this means in this case that the load can be distributed perfectly and evenly across the 4 threads. False sharing is a problem that's not only relevant for OpenMP, it's relevant actually for all shared memory programming models and all computer architectures that work with cache lines. A little reminder, cache line is the basic unit of data, the basic data package that travels between the memory hierarchy levels of a computer. So whenever you need something from memory, and be it only a byte, all you get is a complete cache line, which is usually 64 bytes or 128 bytes. That means that if you load one element, you get the complete cache line, and then if you don't use all the remaining elements of the cache line, there's a lot of waste in data transfer. But that's not the problem here. The problem with cache lines and shared memory programming is, or appears, if multiple threads frequently access the same cache line, and at least one of those threads writes to it. And this is what we call false sharing. In this example, we have an array, and this array is updated. Now, this is very typical for beginners OpenMP code. What this guy has done is they first calculate the thread ID in the parallel region for every thread. Then they initialize an array with a length of OMP get num threads. So there's one element in the array for every thread that's running in the parallel region. These elements are initialized to 0. So far, so good. Nothing evil has happened up to now. Then there's a parallel work shared loop, OMP4. Within this loop, we call a compute function for every loop iteration, and then the result of this function should be accumulated. Now, what is done here is that since each thread has its own entry in the array, the computed X value is accumulated into these entries per thread. So this looks simple enough, okay, because each thread accumulates something into its local or its own element of the array. There's nothing that prevents that. It's a correct program. However, since the number of threads is of the order of between 1 and a couple of tens, these elements that are in the array are usually part of the same cache line or a very small number of cache lines. And this is what happens when a number of cores update the same or update values which are neighboring within memory. So here's core number 1, core number 2, 3, 4, 5, and 6, all updating these array values in rapid succession. Now what has to happen if one core wants to update one element of the array, since data transfer in the cache hierarchy only occurs in full cache lines, it means that the full cache line has to be copied to the cache hierarchy of the core that wants to modify the cache line. Then it can modify the cache line, but in the meantime, a different core wants to update a different part of the cache line. So this just modified cache line has to be written out to the cache hierarchy so it can be read by a different core. Now, if that's all you do, and in our program, that's pretty much all we do. Of course, the compute function could take a long time, but then we actually update the array most of the time. So if that's all you do, it means that these movements of this cache line between one core and the next, between one cache and the next, they cost a lot of time. And this kind of effect, which is called false sharing, can actually destroy the scalability of your code. It can be hazardous. It can lead to the effect that as you add more threads, the code gets slower and slower. It's actually a typical phenomenon of severe false sharing, to have a slower and slower code as you add threads. Now, to make this complete, of course, after the parallel loop, it's still a correct program. Each thread has accumulated a local sum in its own entry of the array. And then in the end, we use a pragma-OMP critical to accumulate all these partial sums into the global variable A. All right. Now, false sharing, as bad as it is, usually if you identify it and you know that it's a problem, then fixing it is quite straightforward. And there are two general solutions to fixing false sharing. The first one is padding. Now the culprit here with false sharing is that all these array elements are so close together. They share one cache line or a few cache lines, so that this cache line has to travel back and forth between the cores of my system. So that's what slows it down. In order to prevent that, all I have to do is to put every array element into a separate cache line, into its own cache line. So I pad the array elements. I leave some distance between one array element and the next. That costs some space, of course, but since the number of threads is typically limited by a couple of tens or something, that's not a lot of memory I'm wasting here. And of course, the minimum distance I have to keep between successive elements is a cache line. As I told you, cache line is usually between 64 and 128, sometimes 256 bytes. So here's the version of the code with cache line padding. Of course, I have to specify what the cache line size is. In this case, it's 8 integers, because integer is my basic data type here, so that would be 32 bytes to keep things simple. Then instead of allocating an array of size OMP get num threads, the size is now OMP get num threads times cache line size. Okay, so times 8 in that example. And everywhere I've previously written ID, I'm now writing ID times cache line size. So this pertains to the initialization, as well as the update, as well as the critical accumulation down here. And this essentially implements the picture on the left, where each thread updates still its own part of the array, but these variables, these parts of this array, are so far apart that each one is in its own cache line, and the false sharing problem is gone. So this is the generic solution to false sharing. Just keep your distance. The second solution, which is probably not as generic, but typically more efficient and leads also to more readable code, is privatization and reduction. And if you look at the code again, you see all what is done here is we call the compute function for every loop iteration. We compute something, and what we compute is eventually accumulated into this summation variable A. So we're doing reduction here. If you recognize that, it's very simple to write this code in a straightforward way that's easier to read and that's usually faster. So here's what it is: pragma OMP4 reduction plus A. We know what reduction does. It gives each thread its own version of A, initializes it with 0 in this case, and then it accumulates automatically into the local variables, and all the reduction into the global version of the variable is done automatically. Okay, so this is really nice. It exposes what's actually done in the loop, and it's much simpler. So the general rule is, and this is not always possible, but if possible, prefer privatization over synchronization. Okay, prefer to privatize data into local instances, which are local to the threads, work on these local instances on their local stacks, and then in the end, reduce them together either with a reduction clause or manually. Of course, sometimes this cannot work. For example, if these private instances would be very large, if each thread would have to get one copy of an array of 1 gigabyte of size, okay, this might be problematic. And this is a case where synchronization may be in order, but always think about replacing synchronization constructs with privatization and or reduction constructs. Okay, let's wrap it up for today. We've learned about locks, which are a fine-grained synchronization mechanism, so we can have arrays of locks, thousands, millions of locks, which is not possible with named critical regions or atomics. We learned about SIMD, which can be applied to simple loops with a SIMD construct, with parallel loops with a SIMD clause, and it can also be applied to functions, which is very attractive if you write libraries that should be called from a SIMD context. Tasking allows you to do more flexible work distribution. It goes beyond loops with the task construct, and task loop allows you to turn loops into a bag of tasks. So task loop is the bridge between loop parallelism and task parallelism. We also covered some performance issues, so overhead, how to reduce overhead. You could just eliminate parallel execution if that costs too much with the if clause. You can also set the number of threads with the num threads clause. If granularity is the problem and you have perfect loop nests, you can use the collapse clause to coalesce perfect loop nests into long loops that are easier to load balance than short loops. And finally, we talked about false sharing, where multiple threads modify values which are adjacent in one or a few cache lines, so that you have a correct program, but the performance implications may be massive. And to solve this, you may employ padding, so keeping distance between one variable and the next, or privatization and reduction, which is often the more elegant and simpler solution to the problem. Thank you.